Good morning, good afternoon and good night to all of those tuning in today. My name is Kerrylee Rogers. I'm a professor in the School of Earth, Atmospheric and Life Sciences at the University of Wollongong. I'm also the Director of the Environmental Futures Research Centre. Today we're presenting on the surface elevation table and marker horizon technique. My presentation complements the following presentation by Torn, who is also presenting on surface elevation table techniques. Here I'll be focusing on mangrove environments, and more attention is given to the installation and measurement aspects, as in the field approaches. Tom will focus more on some of the analytical considerations. The basic premise of the surface elevation table is that you've got a stable benchmark pole against which you can take measurements of relative change in the substrate elevation over time. So you have a pole that's driven to the point of refusal, and on top of that pole a SET instrument is fixed, and the SET instrument can be pointed in different arm directions, and from the SET instrument you lower pins to the wetland surface. You can then come along and take measurements of the height of the pin above the horizontal arm of the surface elevation table. And when you take repeated measurements of the height of those pins over time, you start to see how the surface volume is changing with respect to the base of that benchmark pole. So if you measure your pins in one direction, you have an average value of 10 centimetres of pin height above the table at time 1, and then you come back maybe a year later and take another series of measurements, and the average is now 11 centimetres. You know that in 12 months you've had 1 centimetre increase in the substrate volume over the depth from the base of that benchmark pole. So you get this idea of the increase in the substrate volume from the surface elevation tables. Now, surface elevation tables are always paired with marker horizons. Typically, feldspar is used, and the feldspar is sprinkled onto the wetland surface at the time of the very first SET measurements. As sediment comes in over the top of that marker horizon, it accumulates. You can come back later and take a measurement of the amount of sediment that's accumulated above the marker horizon over time. So say at time 1 we installed the marker horizon, and at time 2 we found that actually there was 2 centimetres of sediment that accumulated above that marker horizon. We know that there's been 2 centimetres of tidally borne sedimentation. So the SETs have told us there's been 1 centimetre of increase in the substrate volume, but the marker horizons indicate there's been 2 centimetres of sediment accretion that's occurred. Now, the difference between those two values, we've got 2 centimetres of vertical accretion from the marker horizon and 1 centimetre of substrate volume change detected using the surface elevation tables. The difference of 1 centimetre tells you what is operating in what we call the zone of shallow subsidence, although I prefer to call it the zone of autocompaction. So this is where processes such as decomposition of organic material and sediment consolidation occurs, and means that the amount of sedimentation that occurs at a wetland surface doesn't exactly correspond to the amount of surface elevation change that occurs over time. Over time, there's been a number of developments in the surface elevation table and marker horizon technique. The first technique utilised lengths of aluminium tube known as irrigation pipe. These lengths could only be purchased in 6 to 9 metres of length, and that meant that the depth over which you could quantify autocompaction and the processes influencing surface elevation were restricted by the length of that tube that you could purchase. Now, that original SET design is shown here on the left. Because of that restriction, there were some refinements that allowed the benchmark pole to be driven right to the basement. And this refinement, known as the deep rod surface elevation table, utilised 1 metre lengths of rods that could be joined together over time. So 1 metre length was driven into the surface, then you connected the next metre and drove it in even further. You kept driving the rods into the wetland surface vertically until they hit the basement geology. Or if you restricted it on the basis of the number of rods you are willing to install. Typically, we start to sort of cut off the number of rods installed to about 30 metres in length, so 30 lengths of rod being driven into the wetland surface. And the premise is that once you're driving 30 metres of length of rod, the overburden volume of sediment means that that rod is unlikely to be moving any further down the sediment profile. More recently, the shallow rod surface elevation table has been developed. The shallow rod surface elevation table has a very short basement. Now, this short basement is designed to characterise the changes happening in the active root zone. So it allows you to disentangle a little bit more detail about those the contribution of organic matter from the below ground biomass to surface elevation change, or decomposition of material occurring within the active root zone. I'll now quickly provide you with an overview of the different surface elevation table types. I'm starting here with the original surface elevation table. This is a technique that I've been using for well over 20 years now. On the left-hand side, we've got an SET being installed at Jervis Bay in Australia. This is actually the very first surface elevation table to be installed in the Southern Hemisphere. It's a much more cumbersome sort of installation process. The architecture around it is much more cumbersome, but since they've been in place for well over 20 years now, they're providing very valuable information that we've been able to validate with other techniques. Let's now move on to the deep rod surface elevation table technique. On the top left-hand side, you can see here the process of installation of the deep rod surface elevation table. We've then got an example of the architecture that's left in place after you've completed your installation. It's quite small, it's not very intrusive, it's hard to locate them over time, so it's a lot less impact visually on a wetland, and also means because of that you're less prone to having any vandalism occur to your surface elevation tables. On that threaded receiver that you can see in that top middle picture, we can place a coupling on which the surface elevation table can be positioned. Now, this surface elevation table has one horizontal arm that we level using this bubble spirit level. Once you've got that horizontal arm leveled, we then lower the pins to the wetland surface. Now, if the wetland surface is very soft and mobile, we may clip them in place just as they touch the wetland surface. And here you can see an example of the pins being lowered and then measurements of the pins being taken, measuring the height from above the horizontal arm to the top of the pin. Now, when we're taking those measurements, we're very careful not to lean on the horizontal arm and to make sure our measurements are as precise as possible. So we measure to the nearest 0.5 millimetre. And here we have an example of the shallow rod surface elevation table. The shallow rod surface elevation table utilises the irrigation pipe that was used in the original surface elevation table. These create 4 legs on which you can place the bracing, and those 4 legs are driven into a sediment depth that allows you to characterise changes operating over that sediment depth. And typically it's done within the active root zone. In coastal wetlands, it depends on the type of vegetation that's in place as to how deep that active root zone is. In the example we've got here, we were wanting to understand the contribution of new mangroves coming into salt marsh areas, and we hypothesised that as those new mangroves are coming in, their roots would not be particularly deep, and so we drove those shallow rod surface elevation tables only to a depth of about 35 centimetres below the basement. You can see the setup of the shallow rod surface elevation table here, and then the measurements being taken. So I've already introduced the concept of accommodation space and that there's a range of processes and drivers that operate within coastal wetlands to influence both the realised accommodation space and the available accommodation space. So you may be wondering how surface elevation table and marker horizon techniques connect to those concepts. Well, they allow you to understand the processes and drivers contributing to surface elevation change within the context of available accommodation space. This means it allows you to understand processes increasing the realised accommodation space. This includes tidally borne sediment accretion, which is detected using marker horizon techniques, and root and organic matter addition and shrink and swell of the substrate, which is detected using the surface elevation table techniques. It also allows you to understand processes increasing available accommodation space. This includes autocompaction and substrate consolidation, root zone collapse and organic matter decomposition, which are all quantified by subtracting the amount of sediment accretion that occurs from the amount of surface elevation change that occurs. From all of this, you can start to build relationships between those processes and those exogenic drivers that may be influencing those processes. This includes things like climate, such as drought conditions, or weather, including the influence of cyclones on substrate conditions, global sea level rise, and geomorphological changes that may have occurred to influence sediment supply. And this is things like water diversions, entrance closure and opening, dredging. There's a whole range of aspects. It also allows you to start to develop broad-scale relationships with processes such as sediment supply, salinity, and tidal regime. What the SET marker horizon technique does not resolve is deep subsidence. This is those sort of geological processes of deep level subsidence. It can be partly quantified on the basis of changes to the absolute elevation of the benchmark over time. Now, this would require you taking repeated measurements of that benchmark pole elevation over time to see how it was moving vertically. Because of our limited capacity to detect those changes using real-time kinematic global positioning systems, it means that actually we can only really quantify profound changes in deep subsidence. At this point, I thought I'd introduce some of the research questions we're using SET and marker horizon techniques for. The first one here, it's one of our most recent installations, is to understand the impact of bushfire on the long-term resilience of coastal wetlands to sea level rise. And you can see here how highly impacted that mangrove forest is by the bushfire that passed through. We've also been using SET techniques to understand the contribution of organic matter additions to mangrove resilience in carbonate settings. And here we're focusing on a low wooded island on the Great Barrier Reef. We've been wanting to look at the effects of tidal reinstatement on processes of surface elevation change. And this is quite topical, as this is one of the activities that can be undertaken to restore carbon additions to substrates, and we wanted to understand the broader impacts of surface elevation change. We've been looking at the processes that influence mangrove expansion into salt marsh in our region, and we've had this program operating for well over 20 years in more than 100 SETs focused on this research question. And finally, we've been expanding upslope a little bit further and wanting to understand the processes contributing to elevation adjustment in supratidal forests. And these are those forests that are just beyond the limit of tidal inundation, that may be inundated once or twice a year, but seems to build elevation so that they control the amount of inundation that occurs. Measurements from surface elevation tables and marker horizons are also useful for parameterising models of the response of coastal wetlands to relative sea level rise. Now, I do need to add some caveats here. If your measurements are taken over short time periods, they really shouldn't be projected forward over very long time periods. And in fact, if you're going to project a model forward, it's likely to be incorrect. So please keep that in mind when you're considering using SET techniques for modelling the response of coastal wetlands to relative sea level rise. Here I'd like like to highlight how some of the information that comes from SETs allows you to understand the response of coastal wetlands to sea level rise. And I've got an equation on the screen that comes from a phenomenal paper by Allen, published in 2000. The basic premise of this equation is that we can understand the relative change in elevation with respect to sea level on the basis of the amount of mineral accretion that occurs, the amount of organic accretion that occurs, the amount of autocompaction that occurs, and the amount of sea level rise that occurs. Here I want to highlight that and we can convert this to become a time-dependent equation. But I really do want to highlight that those first three parameters, mineral accretion, organic accretion, and autocompaction, are defined on the basis of the SET measurement. It's telling you about the substrate volume. The mark horizon technique tells you about what's happening in that tidally borne component, which is largely that mineral accretion. And so you've got all of these parameters that come from SET techniques that allow you to plug them into this equation and understand the response of coastal wetlands to sea level rise. Because a lot of processes influencing surface elevation change is related to accommodation space, it is really critical that each SET benchmark is placed within the context of its tidal position or its relative position within vertical accommodation space. For all of our study sites, we do this using two approaches. We use real-time kinematic global positioning systems to get an idea of the vertical position of each SET benchmark that we have in place. And we also use water level loggers to get an idea of the amount of inundation frequency or the tidal regime at that location. The other thing you need to keep in mind is that it's not appropriate to expect that surface elevation change detected using SETs should equal relative sea level rise. Now, you would expect this if a site was in equilibrium, but we shouldn't expect each low point in a wetland to be in equilibrium with relative sea level rise. To accompany that, we should neither also expect that surface elevation change being less than the amount of relative sea level rise is problematic. High positions in the tidal frame receive less sediment. They have a lot more what we call elevation capital, and this means that they're not yet really vulnerable to relative sea level rise. And it won't be until they get to a position in the tidal frame when the amount of surface elevation change matches the amount of relative sea level rise that they become in balance. Similarly, we shouldn't expect that surface elevation change exceeding relative sea level rise is remarkable. Lower positions in the tidal frame tend to have higher rates of sedimentation. So we need to keep all of those things in mind when we're setting up our experiments.
So we're starting the installation process. We've got our plank and our to cut through the root. But ideally you want to minimise your impact on the soil around that collar, and you just want to take the sediment out. That's where the collar is going to go in itself. We're nearing the end of our rod penetration. We've just gone 30 seconds without any movement of the rod, and so we've stopped and we'll come for another 30 seconds. And so we've got our stainless steel rod that has gone down to resistance, so we know that that's not moving. Now we've got our receiver, which will slide onto that stainless steel rod, and we're going to have 4 screws that go into this to screw onto the rod. And I'll start by loosely, I've got the bottom 2 in loosely. I'll put that in and tighten those up, and then using a wrench, and then once they're tight in place, and this is lowered down. I'll add the other ones later. We've got the receiver firmly attached to the stainless steel rod, and all four of the bolts are connected. We've got the receiver facing the direction we want, and I've replaced the cap because we don't want any cement to go into that notch. And now I'm using rapid set cement, which in dry settings you'd pre-mix this with water, but because the tie's just gone out, there's plenty of water in here, so we're just adding it dry slowly. And so just
Here I'll talk through the installation of the mark horizons. On the left hand side you can see me installing a feldspar mark horizon onto the wetland surface. This is a salt marsh setting. I chose it because it's really obvious to see. You basically sprinkle a few cups of the feldspar onto the wetland surface at the time of the first SET installation measurements. Very rapidly you can see that you start to get sediment accumulating over the top of the mark horizon. Here we have a series of mark horizons that were established at our bushfire impacted site, and you can see their location with respect to the SET installation. So they're immediately adjacent to them. Here we have a series of SET measurements being taken by Dr. Jeff Kellaway. He's lowering the pins to the wetland surface. I'm standing nearby, and Jeff tells me the pin number and the pin length. I tell him the pin length back and record it in a book. Each time we take the measurements in 4 arm directions for each surface elevation table. There's 9 pins along the arm length, and this means that there's 4 directions and 9 pins, so 36 measurements per SET monitoring station. When we're taking measurements of the amount of vertical accretion against the marker horizons at each study site, we tend to take a little mini core from the sediment surface. Here we've got an example of it being taken using a knife to cut around and create a little core shape. Along the bottom here we've got a number of the little plugs of sediment that have been pulled out. You can clearly see the band of feldspar and the amount of sediment that's accumulated above each of those mark horizons. Now we've got different lengths here of sediment accumulation. This is for a study site that the mark horizon had only been in place for a couple of years. This one was in a salt marsh setting, high in the tidal frame, had been in place for a very long period of time. Here we have again another plug. In this case, it was in a mangrove environment that had a very high accumulation rate, nearly in the order of about 25 millimetres a year. There's other ways of collecting your marker horizon data. Here we've got a mini Russian peat corer. It's a fantastic way of maintaining the integrity of the sediment profile, and you can see the little marker horizon in this location here. In more fancy labs, you may have these cryogenic coring systems. Personally, I don't use one. I find them too cumbersome, and we try to minimise the amount of equipment we're having to carry into our wetland settings. So when you're taking your measurements, you definitely want your person who's scribing to repeat each value back to you. You also want to make sure that they're writing the measurements down very clearly. And I've got some examples of some of our field books here. You can see here that we've included a sketch for each SET benchmark location, which indicates the arm direction and where the marker horizons are with respect to the benchmark pole. You should also record as much ancillary information as possible, and this ancillary information is particularly important for understanding whether a pin measurement should be included in subsequent analyses. The reason you may exclude them is because a pin might be falling on a branch that's suddenly protruding into your plot, or on a crab hole, or there's many other reasons why you might need to sort of reconsider the inclusion of that data. So let's now get on to some of the reasons why mangroves might be a little bit more complex. Mangroves have really complex root systems. Here we've got 2 of the really common ones. The top one is the cable roots and pneumatophores from Avicennia species. And the bottom we've got the prop root system of the Rhizophora stylosa or Rhizophora genera of mangrove, you can see that their root structures are quite different. This means that there's varying sizes of root material that's added to the substrate, and depending where your pin lands with respect to that material, the amount of change that occurs will be quite different. We tend to find that mangrove measurements are much more chaotic than salt marsh measurements, where the organic material has a much more consistent form to it. You also need to keep in mind the complexity of the root systems. Here we've got our low wooded isles location. The arm directions are largely positioned on the basis of being able to lower as many pins as possible to the wetland surface. In some instances, we cut some prop roots away to be able to take measurements, but we try to minimise that as much as possible. In this case, we didn't cut any. We did find 4 arm directions that we could get most of our pin measurements in. The other thing to keep in mind is that if you're taking measurements for a long enough period of time, your plot may start to be crowded in with other vegetation that's starting to expand. This image has Tectocornea. It's a salt marsh shrub that grows in southern parts of Australia that's completely infilled this plot. And here we've got another example of Avicennia that's expanded into a salt marsh plot and again crowded in that plot. So that was now a really quick crash course in field techniques for surface elevation tables and marker horizons. I have a bunch of acknowledgements, including the people featured in this video, particularly Dr. Jeff Kellaway, Dr. Kirti Lau, and Professor Neil Saintlin, and there was a whole bunch of postgrad students who've been involved over the past 20 odd years. Our SAT program really got implemented because of the very generous expertise and input from Don Cahoon. He's like the founding father of the SAT technique. Jim Lynch and Nicole Cormier have also been really incremental, fundamental in our SAT analyses. I'd like to recognise the custodianship of the traditional owners on which we do a lot of our research. The Australian Research Council has funded much of our research along with many research partners. I've also included here a few resources that may be helpful. The USGS have a great website that's currently not available, but keep checking, it may become available over time. Thank you.